Hello folks, this is Tom from anti-proton.com, and we're here today to talk about the potato, or rather the radioactivity of a potato. This will be nice and quick, but I've had some people asking me about potatoes and if they're radioactive and if you can detect the radioactivity and that kind of thing. If you see fruit flies going around, it's because I have a fruit fly invasion. Why do I have fruit flies? Again, well, first off, I eat a huge amount of fruit. I'm not a vegetarian per se, but I eat like mostly fruits and vegetables. But there's one right there. Oh, come on now, really? But the other thing too is I've had all these bananas and potatoes down here in the lab I've been testing, right? What happens when you leave bananas and potatoes sitting around? Anybody want to guess? Oh, that's right, you get fruit flies. So I've got little vinegar dishes all over the place trying to get them, and they're almost gone, but they are all coming over here because the lighting that I'm using attracts them. So welcome to the video, fruit flies. Anyway, I mean, I guess they're the most harmless infestation to have, right? At least they're nothing more sinister than a fruit fly. So the question is this: what happens when you see somebody take a Geiger counter, and like this guy's getting 34 counts per minute, and you put it near a potato and you get readings like this? Because I've seen this. Well, I have to first question what's the likelihood of it, because the reason I'm getting these readings is I have a check source underneath the potato. If I get rid of this cesium-137 check source, this potato doesn't tick like that anymore. Now you see the screen hasn't updated on the Geiger counter. It still says 136 counts per minute. But you can tell from the ticking it's not anywhere near that high. It's basically background. And in a few moments the Geiger counter will respond. Come on now, really? Do you have to be that slow? But anyway, so it's getting there. I'll just put this here and let it kind of sit. There, it's dropping. If you took a whole bunch of potatoes, there it goes, down to normal. If you took a whole bunch of potatoes, dozens of potatoes, and put the Geiger counter on them and ran it for like maybe 8 or 9 hours and did a statistical type analysis, you'd probably detect a little bit of radioactivity from them. They are radioactive. But nothing like that. So when you see that, you should be skeptical. Did that potato come from Chernobyl? Did it come from Fukushima? Because I can't imagine too many other reasons why you would detect it coming from, like, you know, the actual potato itself. Same with it goes for bananas. Anyway, so there are plenty of things in your house that are radioactive that you can readily detect, like the porcelain on your toilet seat and just about any granite countertop that exists. Things like that are easy to detect, but not usually potatoes. Now the reason a potato and a banana and anything else with potassium in it is radioactive is because it contains potassium. Well, that's kind of a circular statement. But anyway, so basically put, potassium is natural. It exists all throughout the environment. It's in your body, bananas, and all kinds of stuff. So potassium has, the actual element potassium has many different isotopes, equal members of being potassium. The only difference is that they have different numbers of neutrons in them, right? Some of them have more, some have less, but they're all still potassium, right? Potassium 39 and 41 are both stable, and they're found everywhere through nature. But potassium 40, the little guy right in the middle, is not stable. And there's a tiny bit of it in every single pinch of potassium. And that's why if potassium's in a potato, by definition, potato must be slightly radioactive. But no, not by much. Potassium at 40 undergoes all three forms of beta decay. It undergoes beta minus, beta positive, and electron capture. So it's emitting gamma rays. About 10% of its decays result in a gamma ray, plus or minus. I mean, you guys aren't physicists, so I'm not going to say 10.7244. I'm just saying it's about 10%. I mean, you look it up if you want. So if since we're not going to get anything from this potato, let me just quickly show you some potassium. So here's a coffee filter. Notice the coffee filter does nothing. Notice that this does nothing because we're not fooling you. See? Not fooling you. Oh, come on now, really? Right when I put this over, it ticks a little bit. Well, not very much, and this is going to tick like crazy in a minute. So now we're going to take this, a can of light salt, potassium chloride sodium salt substitute. It's a lot of S's. So this is 690 milligrams per every 1.4 grams. So it's less than half potassium. So potassium chloride even. So we'll pour this into here, and let's see what we get when we measure this. Now this is potassium. You eat this. I put this on my food. I actually pour potassium chloride stuff like this on my eggs in the morning, and I'll put it on other food too. So like I eat this, and I'm not dumb to do it because you need potassium. It turns out if you don't have potassium, you'll die. But anyway, got to get it really close. And as you can see, potassium is quite radioactive. Oh, not quite. I mean, this isn't exactly like a plutonium slab or something like that. I mean, but it is reasonably radioactive, more so than background. So far, it's about 6 times, no, 3, 6, 9 times background, 10 times, 11, 12, 13 times background-ish, somewhere in there, 14 times, 15 times, something like that, if my math skills are going quickly enough. You get the idea. If we can push a little over 500 counts per minute, but I'm not going to try to get this close enough and hold it for long enough. So I took one of these and threw it in the gamma spectrometer to see if I could get a spectrum of potassium 40 from one potato, just one potato. The first time I did it, I failed miserably because the potato had so little potassium I couldn't detect it. One of the reasons for this is because the different soils that they're grown in have different levels of potassium. But this little spud right here, this guy right here, it's the one that worked out fine. It had lots of potassium. It was potassium rich, tasty, super duper. So I threw it inside the lead testing chamber. I put a 1.5 inch sodium iodide thallium dope scintillation probe against it and ran it for 4 hours using gamma spectroscopy. Now let me show you what I found. By the way, I did not do a quantitative analysis of the amount of potassium that is in this, but it wouldn't matter if I did anyway, because that would be just this potato. Every potato is going to be completely different. But I did do a bit of estimation as to how much potassium one would expect to find in this container, a banana, and a potato, just to give you kind of an idea. So I'll explain that in a minute when I yap about the gamma spectrum. So otherwise, here we go. Okay, folks, so here we are on the spectrometer. We have 1,024 channels across the bottom, so 0 to 1,023 over here. And every time a gamma ray is detected by the detector, the gamma ray is deposited in one of these little channels, which slowly arise as they count up. Each one of these is like a little channel. And they're deposited by energy. So low energy are down here on the left, and higher energy are up here on the right. Now we start at 10 kilo electron volts, which I always say kilo electron volts because that's kind of the way I say it, and I sort of mispronounce it, and I always do that and always have and probably always will. But anyway, so that's thousands of electron volts, and we go all the way up to 3,504 kilo electron volts, so that's 3.5 MeV. All right. Now we can look and see, here are the counts, by the way, on the sides. Like, for example, this guy right here, this channel number 23, for example, which is approximately 72 kilo electron volts, it has a count of 1,897 gammas that went in that one channel. So you get the idea, and then it just kind of goes all the way along here, and you see the little numbers changing. So let's look and see what we have in the spectrum. So right off the bat, we have the lead fluorescence from the testing chamber. We use lead to shield ourselves from the background radiation, but it itself fluoresces, kind of like a white t-shirt with a black light, except in this case it's X-rays, and the lead is serving as the white t-shirt. All right, so moving on along, right around here, we're at 511 keV. So this right here, that's the rest mass of an electron. So this guy right here is coming from most likely not potassium, but positron decay. So basically, put a positive beta positive particle, a positron, it's an anti-electron, is annihilating with a regular electron, and the two of them are emitting 511 keV gammas, which we're detecting here. So that's a little bit of antimatter, most likely. I mean, I'm not going through this and super checking because I only cared about that little bit right there, so I wasn't looking at the rest of it. I'm just kind of eyeballing it. So we're not being too scientific. Let's smooth this a little bit. This right here is probably uranium at bismuth 14 at 609 keV. That's probably showing some uranium that might be in the potato. Might be in the background too. And this guy right here, this is the most important part. 1461 keV, this is the potassium peak. This is coming from potassium. This is the signature of potassium. Now, is it from the potato? Who knows? This guy right here might be a Compton peak. Yeah, that's looking like a Compton peak. And that's probably like protactinium or something. So basically, this is the one that's important right here. This is the potassium that's found in the potato or in the natural environment. It's in my body, it's in your body, it's in the walls, it's in everything. It's all over the freaking place. You cannot get rid of potassium. It's everywhere. And it's such strong gamma rays that come from it that it penetrates and goes through everything. So it's very, very hard to shield it. Now, I was displeased because what I did was I loaded a background spectrum. See? So 8-hour background. And then when I stripped it, nothing's left. Smooth. And if you look, you see that 1461 keV peak is gone. That angered me because I spent all that time. The only thing that was still there is this, whatever this is. Centroid 27. It's probably a little bit of uranium from the potato. That's probably like lead 214 or something like that. It's right around the right area to be maybe that. But the thing I wanted, the 1461 keV potassium is gone. What am I to do? Well, here we go. This is what I'm looking for. A nice solid potassium peak. See, there's the Compton edge. There's the Compton plateau, the backscatter peak, and that right there is the potassium 40. That's what it should look like. And this comes from the little can of potassium that I tested for 1 hour. So I ran it again on a different potato. I ended up with this. for 4 hours I ran it, and I get this little stupid peak, and I'm thinking to myself, oh god, this looks worse than the other one. How am I going to detect anything? But when I just subtracted the background from it, like I showed you a minute ago, look at that! There's still plenty of it left. That means there was a rich amount of potassium in that potato. The other potassium came from my background, but this came from the potato, as you can see. So in this whole area of the potassium from the potato, I had a net of 182 counts above what would be expected to be in this area based on the rest of the sample. So gross was 245 counts. So that 182 counts, 182 detected gammas in this area over 4 hours is not much. So this detector is tremendously more sensitive, vastly more sensitive than a Geiger counter. So I don't think you're going to detect this with a Geiger counter. Now to give you some ideas, that can of light salt was, I estimate that it was probably around 1,350 becquerels. That's 1,000. When I say a becquerel, that's a decay per second. So 1,350 decays per second of potassium 40 plus or minus. And this is based on the amount of potassium that's in the can and the amount of potassium that's normally found in the real world, that sort of thing. So it's somewhere around there. The banana, for example, has around 14 becquerels, about 14 decays per second, plus or minus. The potato, I've calculated that the potato on average has probably about 20.65 becquerels, 20.65 decays per banana per second, per potato per second. Sorry, I keep switching potatoes and bananas, right? So a potato should be about 20, almost 21 decays per second. Now, I'll show you the math up on the screen here of how I came up with that. But what it boils down to is pretty much an undetectable amount by a Geiger counter by any normal means, except maybe a very long timed analysis with a lot of potatoes. So in the end, potassium is good for you, but it's also radioactive. Potatoes, bananas are good for you, but they're slightly radioactive, and you're not detecting them with anything outside of laboratory equipment in any sort of real sense, okay? So at nearly 1,300 becquerels, plus or minus, so that's decays per second, that we're undergoing in this little can here, this cesium-137 check source is a mere two and a half times as radioactive as this. And when we're talking about numbers of decays per second. Now when we're talking about gamma rays, this one's putting out more. But 7 or 8 of these, maybe 9 of these little tubs, like a pack of them, like a little 12 pack, would probably be putting about as many gamma rays as this little guy here. And the other interesting thing is that the gamma rays that come from this are 662 kiloelectron volts. These guys right here are 1461s. They're much stronger. They have more penetration power. They can go farther distances and that sort of thing. So I always get people saying, oh, you'll have cancer by tomorrow with this. Oh, it's destroying you. How could you touch this with your bare hands? But at the same time, first off, it's completely sealed. But second off, the gamma rays coming out of here are weaker than these in power. And 7 or 8 of these little cans sitting around, which most people wouldn't blink an eye at because it's just light salt, right? It's just potassium light salt, has the same radioactivity. And they're the same exact material coming out of these things, in this case betas, so beta positives, beta negatives, and their counterpart neutrinos. There's no difference. In fact, this actually has more energy, so it's more likely to go through my hand and that sort of thing. So this is kind of an interesting thing to think about. By the way, I am aware that if this were actually unsealed, that cesium-137 can have a longer biological half-life than this. So if this were in your body, it would be a problem. But outside of your body and sealed, they're pretty similar to one another. 7 or 8 of these guys compared to one of those guys. Cool, huh? This is Tom from anti-proton.com, and make sure to take in your potassium. Yum, yum, yum.